Welcome. This is a video presentation of the paper, A Universe from Itself, the Geometric Mean Expansion of Space and the Creation of Quanta, Part 4. In this part we're going to look at the large and small delta values, show that uncertainty relations are geometric mean equations, show the Planck relation is a geometric mean equation, and show how to easily create uncertainty relations. Let's start with the large and small delta values. Let's calculate delta R small. Using the geometric mean relationship, delta R small times delta R large will equal the initial radius squared. Calculating delta R small gives us 2 times g h bar over c to the fourth, because we know that this value here is equal to 2c, and we can plug it into the equation here. Numerically, delta R small comes out to about 1.7 times 10 to the minus 78th meter seconds. Let's now calculate delta E small. Using the geometric mean relation, delta E large times delta E small will equal the initial energy squared. We'll rearrange, plug in our value for delta E sub O, which we determined previously, and we find that delta E small is equal to h bar over 2. We'll follow the same procedure for calculating delta mass small. Using the geometric mean relationship is equal to the initial mass squared. Rearranging, plugging in our value for delta m sub O, change of mass for the entire observable universe, is equal to h bar divided by 2c squared. To calculate delta t small, we will multiply delta t small times delta t sub O, and it'll equal the initial time squared. We know the initial time squared is the Planck time squared. Delta t sub O is also the Planck time squared, so delta t sub small is equal to 1. No dimensions, just the number 1. This table is a summary of the large and small delta values. This column's our large delta value. This is the column for our small delta values. We have delta radius, delta energy, delta mass, and delta time. We plugged our values in that we've already calculated here. Some of them were calculated earlier. And this column over here represents the initial values, the geometric means of the expansion. We can use these delta values to create additional uncertainty relationships. For example, small delta energy times large delta time gives h bar over 2 times 1, or h bar over 2. Our value of h bar over 2 for the small delta energy and large delta time matches what we've already done with delta energy of the observable universe times delta t sub O, which is the Planck time squared. Multiplying these two values here gives us the same value we just got. We can cross-multiply to get uncertainty relations. For example, large delta time against small delta energy gives h bar over 2. Conversely, large delta energy times small delta time also gives h bar over 2. Let's examine this further. From the previous table, we find there are 6 possible cross products. For example, delta radius times delta mass is equal to h bar over c, and delta t times delta E is equal to h bar over 2. And we will make the claim that these are uncertainty relationships. To make it clear, this column represents the product of delta values. This column gives us a large value times a small value, and this column is a small value times a large value. For example, delta t times delta E is equal to large time times the energy of what we're going to call the small energy quantum, which is equal to our unit of small time times the energy of the observable universe. They all equal h bar over 2. And we find the case applies to all of the other items on this list here. The uncertainty values, such as h bar over 2, or h bar over c, or h bar times c, are the products of the initial values. Here we see that if we take initial values, for example at the bottom here, if we multiply the initial time against the initial energy, we get our uncertainty value, h bar over 2. So whether it's delta time against delta energy, or large time against small energy, or small time against large energy, we get h bar over 2. And at the top, if we multiply the initial radius against the initial mass, we find h bar over c, which is what we get if we multiply delta r times delta m. And the case applies down the list of all 6. Let's look at the relation between radius and mass. We know that delta r times delta m is equal to h bar over c, and so is the radius of the hyperverse against our small energy quantum mass, and our small radius times the mass of the observable universe. We can rearrange these three equations so that delta r is equal to h bar divided by c times delta m, or that the radius of the hyperverse is equal to h bar divided by speed of light times the mass of the small energy quantum, or a small radius is equal to h bar divided by c times the mass of the observable universe. All three of these are Planck relations. In switching from delta m to delta E, we find that delta r times delta E is equal to c times h bar, and so is the large radius against our small energy and our small radius against our large energy. In rearranging, we find the same relationship before. All of these are Planck relations. The conclusion is the Planck relation is a geometric mean equation. Looking again at our 6 equations of the products of delta values, delta m and delta E in this case against delta r, give us Planck relations. We've seen that delta T times delta E equal to h bar over 2 is the time energy uncertainty equation. And again, we can change it just by changing from delta M to delta E so that these two are related. This leaves us with 2 to look at, and we're going to start by looking at delta M times delta E. If we take delta M times delta E, we get our expression. But these two are deeply related. We can get the energy just by multiplying the delta mass by c squared. So if we divide both sides by c squared, we get 2 delta m's multiplied by each other, so that'd be squared, and we get the initial mass squared. The bottom line is that there's no significance to this particular uncertainty relation. It's a different scenario here. As we've seen, delta time times delta radius is the same as large time against small radius, or small time against large radius. The product of the two is this term here, which matches our delta r sub s. Numerically, delta r sub s is approximately 1.7 times 10 to the minus 78 meter seconds. If we divide both sides by 2, specifically delta r divided by 2, and our product by 2, we find that the product of these two equals big G times h bar divided by c to the 4th. If we divide delta r by 2, we get delta length, which we'll show as delta x. This is our position function. To help clarify why 1/2 of the radius is a length, recall in the initial condition our initial radius was 2 Planck lengths, but our initial length is 1 Planck length. So switching from radius to length, we find that delta t times delta x is equal to big G times h bar over c to the 4th. And we're going to claim that this is the time-position uncertainty relation. And numerically, the product is about 8.7 times 10 to the minus 79 meter seconds. We can do the same thing with the relation between energy and position. We know that delta r times delta E is equal to c times h bar. If we divide delta r by 2 on this side and c times h bar by 2 on that side, we find that we get delta x times delta E is equal to c times h bar over 2. This is our position, and therefore we can claim we have a position-energy uncertainty relation. Delta x times delta E is equal to c times h bar over 2. So rather easily, we just created two uncertainty relations, our position energy and position time relation. So do uncertainty relations really exist? What is their meaning? It's not as clear and obvious as it might seem. Let's look at a quote by John Baez, physicist. And this is regarding the time-energy uncertainty equation. He says, "There's an energy operator in quantum mechanics, usually called a Hamiltonian and written H. But the problem is, there is no time operator in quantum mechanics. This makes people argue a lot about the time-energy uncertainty relation, whether it exists, what it would mean if it did exist, and so on." The hyperverse model tells us that uncertainty relations are geometric mean equations relating the large and the small of the universe. The limit of an uncertainty relationship is the product of the initial values of the universe.